Hello there and welcome back. We are starting now our first part of a lesson on something called refraction and lenses. So last lesson we talked about reflection, and we learned that reflection is the thing that happens when light travels into a new medium. Some of that light is going to be reflected. Well, the other thing that can happen is that some of the light could refract or travel into the new medium. So an example of this would be water waves. The speed of a wave is going to depend on the medium. Now, it turns out that in the ocean, waves travel faster in deep water and then more slowly as the water gets shallow as you approach the shore. So if you were to look like kind of bird's eye view at a bunch of ocean waves as they travel along in the water, you might say they're nice and evenly spaced out. But as you start to approach the shore, well, then the waves slow down. And so what you'd start to notice is the waves kind of become packed more and more closely together, right? And the depth of the water is changing how fast the waves moves, and so now all the waves kind of get packed up one beside the other. So if those waves are just traveling like straight towards the shore, that is to say, if the angle of incidence is 0, then they just continue straight into shore. But a couple of things do change. So for example, if you think about like this laser that I'm shining here, you can see this laser travels from air into glass, or sorry, into water. And so it doesn't look like much is happening because it's just a laser in both. But if I take a look at what's happening with the waves, what you should notice is that the waves here inside the water are a little bit more piled up. And so they've also slowed down. Now, if they're more piled up, that just means they're closer together. And so what's changing here is the wavelength. So we know that V equals lambda F. And since the medium changes, the speed changes. And then the other thing that changes in response to that is the wavelength. So the velocity changes, but the frequency stays constant. And that's important, okay? So the wave still has the same frequency, and we're going to learn later that the frequency of the wave is related to the energy. So the energy isn't lost by the wave because it has the same frequency, but the wavelengths change as a result. So the wavelengths change as well. Now, what happens if the waves are not traveling straight towards that new boundary? If they travel towards the surface but at a bit of an angle? Well, what we're going to see is that they're also going to bend in that case, okay? And so we can see an example here. If I take my ray and I kind of go like this, you can see that as I approach a new medium, I travel into the new medium, but I'm also going to bend. So for those of you that are like classic rock fans, you might notice this picture here, that the light ray travels into a prism, and then it bends when it hits the prism, and then when it leaves the prism, it bends again. This actually leads to one of the reasons that prisms are quite interesting, because when we shine pure white light at a prism, what we'll see is that actually the prism separates the light out into its constituent colors. This is kind of how we first discovered that light is made of different colors, that white light's made of different colors. And so essentially the reason for that is that the different wavelengths of light bend just slightly different amounts when they go through the prism. And so because they each bend a slightly different amount, they kind of separate out into their constituent colors. And so because of that, we have rainbows and other nice things. So keep in mind though that the amount of bending that's going to happen is going to kind of depend on the angle that I come in at. Okay, so there's two things to notice. The steeper the angle I have here, the more the kind of change in the bend. The other thing to notice though is that I still get reflection. So when I hit a new medium, I still get that reflection that we learned about before. It's just that in this case, some of it reflects and some of it travels through into the new medium. You might notice that the steeper the angle that I go at, the steeper the angle, more and more of it gets reflected and less of it actually travels into the new medium. So that's kind of interesting too. So let's get some notes here. So what is refraction? Well, refraction is essentially the bending of light rays when you change medium. So bending of light as it changes media. Okay, and again, the reason for that bending is because of a difference in speed. Okay, now the optical density of a material, so light doesn't travel through everything, so not everything has an optical density, but if it's translucent or translucid, then it's going to allow light to travel through at different speeds. And so the optical density gives you an idea of how difficult it is for light to travel in a medium. So each medium is going to have a different optical density. Air is different than glass, is different than water, is different than diamonds, and so on. Okay, so imagine we're shining a laser into a piece of quartz here, okay? You can see that the incoming ray is going to strike the quartz at an incident angle, just like we learned before. And the incident angle, again, is going to be measured relative to the normal. So the angle of incidence is this angle here between the normal and the incident ray. And we know that some of that is going to reflect, so that's nothing new. It's going to reflect, and it's going to follow the law of reflection. So your angle of reflection is going to be the same, but some of it is going to refract, and so it's going to bend, in this case, towards the normal as I go into the new medium. And so this right here is my angle of refraction. Now we give that the symbol theta r, but we use a capital R for the refraction and a small r for the reflection. So keep in mind that just like we did with our reflection, we need to measure our angles from the normal, because the normal is that line perpendicular to the surface, and it's going to give us a nice standard thing to measure against. Now, Snell's law is a formula that allows us to calculate how much bending is going to happen, and of course, it's going to depend on the optical densities of the two media that you're traveling into and from. So Snell's law says Ni times sine theta I equals Nr times sine theta r. Now, obviously, theta I and theta r are our incident and refracted angles, but the n's in this equation here, Ni and sine, and Nr, this is something called the index of refraction. Okay, and it's just a number that tells us kind of how slowly the speed with which light is able to travel through that medium. So notice that the direction of bending is going to also depend on which way you're going. So if I jump back to my example here, in this case, I'm going from air into water. So I'm going from less dense into more dense. You can see the index of refraction of air is about 1, and for water, it's about 1.33. So I'm going from less dense into more dense. And so we need a way to describe which way the light is going to bend. And we can't say kind of up or down or left or right, because that's going to depend on which way we shone the light in the first place. So what we say in this case is I go from less dense to more dense. You can see that the angle of refraction is smaller. That means that I have bent towards the normal. So when I go from less dense to more dense, I bend towards the normal. Now let's flip this around, okay? Let's change this to air, and let's change this top material to, I don't know, glass, for example. So now you can see as I go from glass into air, as I go from more dense to less dense, I'm gonna speed up when I hit that new medium, and I'm gonna bend away from the normal. So from more dense to less dense, I bend away from the normal. All right. So let's just make a quick note of that. So less dense to more dense, it's going to slow down and bend towards the normal. When you go from more dense to less dense, it's going to speed up and bend away from the normal. Okay. Now, we should just make a note of a couple here. Now, you don't need to memorize these, but it's just kind of handy to have, and we're going to use them down below to know that the indices of refractions for a few things. So a vacuum, the index of refraction for a vacuum is exactly 1. That's actually how we define an index of refraction. And air is very, very close to a vacuum. It's actually 1.0003. So for all intents and purposes, we can treat air like a vacuum in most cases. Water, we saw that was like 1.33 approximately. It's going to depend on the temperature and a few things about the water. And then glass, again, depending on the type of glass, is probably somewhere around 1.5. So hopefully you get a sense for your index of refraction that it's going to be a number that's more than 1, but not necessarily much more. All right, so we've got a ray of light traveling in air, and it strikes a block of glass at an angle of 35 degrees. Find the angle of refraction and draw a picture. Okay, exciting times. So I'm going to just sketch out a little diagram here. I've got a block of glass, and it's helpful to kind of just draw in our normal line. So we've got a normal line that goes through. And I got my incoming ray here, strikes the glass, and this is like a 35-degree angle. And I'm already short on space, but that's okay. Now think about this. As that light comes in, it's going to slow down when it hits the glass, and the slowing down is going to cause it to turn and bend towards the normal. So this angle right here, my theta r, I'm expecting that to be smaller than 35. Otherwise, something's gone wrong with my calculations. So ni sine theta I equals nr sine theta r. And then I just have to do some algebra to solve here for theta r. And you can see theta r is going to equal inverse sine of ni over nr times the sine of theta I. Now plugging in all of my values, I get inverse sine. Now for air, you could probably just use 1, but maybe I'll just use 1.0003. I don't think it's going to make much of a difference. Over, what are we, glass? So that's 1.5. And I can multiply that by the sine of 35 degrees, and I'm going to make sure my calculator is in degree mode and not radians. And when you kind of crunch that all out, we get an angle of 22 degrees, which again makes sense. And this is where drawing the picture ahead of time is going to be helpful, because it just kind of sets the frame. So you're like, yeah, I'm expecting it to be smaller than 35, and what do you know, that's what I got. So I'm feeling pretty good about that answer. All right, try another question here. So now we're going from underwater into air. Okay, so we've kind of got some water here, and then we're traveling in the water, and it's bouncing into air. So I've got a normal line like this. Okay, now in this case, what they've told us is the refracted angle. So I know that once it bounces into air, the refracted angle here is going to be 65 degrees. And that's my angle of refraction. And the question is asking, well, what was the angle of incidence? Well, if I'm going to go from water into air, from more dense to less dense, I know that I'm going to bend away from the normal. So my initial or incident angle should be less than 65. So theta I should be something less than 65, and then I bend away from the normal when I travel into air. Okay, so it's the same formula, same Snell's law. Ni sine theta I equals nr sine theta r. And we're just solving for theta I in this case. So it's actually going to look really similar to the last question. So it's going to be inverse sine of nr over ni times sine theta r. Okay, so plugging in all my numbers, inverse sine. Now the refracted index in this case is air, so that's 1.0003. And I'm going to divide that by 1.33 for the index of water, and multiply that whole thing by the sine of 65 degrees, because that's my refracted angle. Okay, and when you crunch the numbers and put that all in, you should see that the incident angle is right around 44 degrees, which again, that makes sense, that it's less than the refracted angle, which was 65. Okay, so just a couple more things really quickly. We're just going to define our index of refraction. And so our index of refraction for any given material is going to be C divided by V. And so N, of course, is the index of refraction for that material. C is the speed of light in a vacuum, which remember is the fastest that light can travel, and that's right around 3 times 10 to the 8 meters per second. And then V is the speed of light in the medium. So whatever the thing is that we want to know, the glass, the water, the air, the whatever. So the question is, what is the speed of light what is the speed of light in water? So N equals C divided by V, which means that V equals C divided by N, which is 3 times 10 to the 8, all divided by 1.33, the index for water, which gives, and this all works out to be right around 2.3 times 10 to the 8 meters per second. So it's useful to see here that yes, light does slow down when it travels into water, but it's still like very, very incredibly fast, right? Like there's no material that we have that could slow down the speed of light to some really small amount that we might observe. Okay, one last thing that we want to talk about in this first part of the video is something called total internal reflection. Now, this is kind of a funny situation that can occur if we're ever going from a more dense to a less dense medium. Okay, and so imagine this laser is like traveling along in the glass and it strikes the surface of the glass and it goes into air. Now, we know that it's going to bend away from the normal, okay, because we're going from more dense to less dense. Well, what happens if we increase that angle? Well, if I increase that angle, then it's going to bend. Well, it's going to bend more, right? Like it's going to bend away from the normal, but it's going to bend even more away from the normal. So I might get something like this, okay, an even steeper angle. We'll just take that to its logical conclusion. Since the refracted angle is larger than the incident angle, then there would be some point that I could go to where the refracted angle is going to be 90 degrees, right? You could have some like magic angle that if you go in at just the right angle here, when it refracts at 90 degrees right along the surface here, right? And then so the question is, well, what if you go past that point? Okay, so this particular angle, this incident angle that gives me a refracted angle of 90 degrees gets a special name. We call this the critical angle, theta c for the critical angle. And so it begs the question, what happens if you just go a little bit further? What happens if you go beyond the critical angle? Well, it's actually a little bit surprising. So I'm going to use this as my example here. So you can see I'm going from glass into air. And you can imagine that as I go steeper and steeper angles, you can see my refracted angles getting bigger and bigger. And on my critical angle, it happens somewhere around here. And it kind of disappears. The ray is now gone. So what happens? Well, once we get to that point right there, notice that none of the light can refract, which is none of the light can travel into the new medium. Now, what's been happening the whole time, of course, is the light has still been reflecting because it's always going to be both, right? Some will reflect and some will refract, which is hard to say, one after the other. But both things are going to happen. Well, once we go beyond that critical angle, we get to this point where all of it just simply reflects. And so this is what we call total internal reflection. Now, this is kind of a weird phenomenon because you might start to wonder, like, what is the light even bouncing off of? It seems strange. It's bouncing off the interface between the glass and the air. It's kind of bouncing off air. We think of air as normally being pretty like easy to travel through. But regardless, we get a complete bounce. And so it is total in the sense that like all of the light bounces off. And this phenomenon is what we use to build things like fiber optics and send messages through glass cables with really good resolution, because all of the light is going to bounce off and stay inside the glass. If you had a big long piece of glass, you could bounce the light on and on and on for a great distance. Okay, so our total internal reflection, our first thing, our critical angle. The critical angle is the incident angle where the refracted angle equals 90 degrees, right? So it's the critical angle is where you just get to the point where you're going to refract, you would refract at 90 degrees. And total reflection happens whenever the incident angle is greater than or equal to the critical angle. So all of the light is just going to reflect back in whenever you're past that critical point. So find the critical angle for light traveling from water into air. All right, well, we'll draw a diagram. Okay, so we're going from water into air. All right, I got some water here. I'm gonna draw some nice flat still water because otherwise that would mess with things. And I'm gonna draw my laser going along here, and it's going to bounce 90 degrees right along the surface. And don't forget my normal line, and then there's my critical angle there. So using Snell's law, Ni sine theta I equals Nr sine theta r. But at this point, it's worth considering, well, what's going to happen with sine theta r? My refracted angle is 90 degrees. And the sine of 90 degrees, well, that's just 1. So actually, this whole term is going to go away because the sine of 90 is 1. And so to solve for my critical angle, theta I is just going to equal inverse sine of nr over ni, which is inverse sine of air, 1.003, over water, 1.33. And this gives me a critical angle of right around 50 degrees. Okay, so any angle beyond that, we're going to get total internal reflection. All right, that is it for part 1 of this video.